It's my great pleasure today to introduce our next speaker, who's Bronwyn Hajek. Bronwyn's an associate professor at University of South Australia. Bronwyn's been a member of both the New South Wales and South Australian state teams in large bore rifle shooting. And that includes at least one national title that I'm aware of. So just like Pierre-Simon Laplace, she has an interest in ballistics. And like Laplace, she also has a strong interest in partial differential equations. Bron's been a willing worker for ANZIAM and the engineering maths group for many years, ever since she graduated. In fact, she convened the very first early career researcher conference for the Australian Maths Society. Bron has multiple ARC grants. She's a very versatile researcher with strong papers in biological maths, physical electrochemistry, and symmetry methods for partial differential equations. And I think she will speak on at least two of those topics today. So thank you, Bron.
All right, thank you, Phil, for that lovely introduction. I'm very glad that you were introducing me. And first, I'd like to thank Matt Simpson and his Invited Speakers Committee and Michael Small and his organising committee for inviting me to speak. I'm really happy to speak at ANZIAM. I've been coming to ANZIAM for a long time, and it's nice to give an invited talk here. So my research, not all of my research, but a large chunk of my research focuses on constructing exact analytic solutions to nonlinear partial differential equations. And typically I do that using the tools of symmetry analysis. So I'm going to talk about these things today in my talk, and I'm going to talk about them in the order in which I've listed them in my title. So first I'm going to talk about reaction-diffusion equations, what they are, when and why you might use them. Then I'm going to talk about symmetry analysis, and I'm going to talk about symmetry analysis in quite a lot of detail because maybe I'm a little bit strange, but to me this is where the fun is. It's in the actual mechanics of solving the differential equations. So I want to show you that. And then I'm going to talk about two solutions that we've found for a couple of problems in the past. What I really want to do is give you some kind of sense about what symmetry analysis can do and why analytic solutions are important and useful. Now, I've got a little 18 after my name. It's not because I'm 18 years old. I wish I was. That little 18 is especially for you, Scott. It is signifying that I've been coming, this is my 18th ANZIAM. And Scott's been trying to convince people for years to put a little number after their name that says how long they've been coming for. So that one's for you, Scott. Okay, now I can't change my slide. There we go. All right. So these are reaction-diffusion equations. This is what they look like. They're evolution equations that are second order in space. They have a diffusion term, so they can talk about things that are moving around. And they have a reaction term. So the reaction term could be a source or a sink, so production or consumption. And it's often used to represent things like maybe a chemical reaction, or maybe births and deaths in a population, or perhaps cell proliferation or something like that. And U, the dependent variable, can be used to signify things like the concentration of something, or maybe population density and things like that. So these are the types of equations I'm interested in, and I'm particularly interested in ones that have nonlinearities, either in the diffusivity or in the reaction term. Okay, so I'm going to try and give you a bit of history of all these things along the way, because I think that's a little bit important too. So these kinds of equations, I guess, first started to become used more commonly in about the 30s. In fact, there was two really well-known papers published in 1937. They're published independently, but in the same year. One of them was by Kolmogorov, Petrovsky, and Piskunov, and I've got a picture here of Kolmogorov and one of Petrovsky on a stamp, no less. I couldn't find a picture of Piskunov. Kolmogorov, who incidentally, he was the editor of the maths section of his school newsletter at age 5. I don't know what you were doing when you were 5, but I wasn't editing school newspapers. Kolmogorov was working with a population geneticist in the USSR, and that was kind of a risky business back then because Stalin had been convinced that genetics was just pseudoscience, and a number of geneticists were executed or sent to labour camps. So that was a bit of a risky business at the time. This is their paper here underneath their pictures. That's just the diffusion equation. Later on, they add their reaction term. And the equation they were looking at had a constant diffusivity and a polynomial reaction term. So the other paper that was published that year was done by Fisher. Now, Fisher was also looking at a problem in population genetics, and he published his paper. He was using equations that had a constant diffusivity and a reaction term that was quadratic. So I had a U, 1 minus U term, and that's the standard kind of logistic term that lots of people use these days. And so this class of equations has become known as the Fisher-KPP equations. And I've seen a few talks this week at this conference that have been talking about Fisher-KPP equations. Now, this is the first picture of a man with a beard. It won't be the last picture of a man with a beard. So if you'd like to play along at home, you can count up the number of bearded men photographs in my talk. Okay, so these kinds of equations have been used since the 30s to describe all kinds of things. They've been used for problems in heat transfer, chemical reactions, flow through porous media, but they've been used extensively in maths biology. So looking at things like population dynamics, population genetics, cell proliferation, all sorts of problems on that kind of front. Of course, you can also get systems of these equations, so multiple component ones, and they're often used in pattern formation or perhaps prey systems and things like that. I'm only going to talk about scalar problems in my talk, so just one equation, not systems of reaction-diffusion equations. Okay, so I'm particularly interested in equations like this that are nonlinear. So they have a nonlinear diffusivity or a nonlinear reaction term. And these kinds of equations are almost always, not always, but very often solved numerically. And that's because they're hard. But this is why I like them. Right? I think they're fun. They're a bit crazy. Some analytical solutions do exist and are well known. For example, if you have Fisher's equation, so constant diffusivity and a quadratic reaction term, then you can find travelling wave solutions to those equations. So some exist, but not many, and most people solve them numerically. All right, so that's what I'm going to say about reaction diffusion equations for now. Now I'm going to start talking about symmetry analysis. That's the next beard. So symmetry analysis was developed by a Norwegian mathematician, Sophus in the late 1800s. By all accounts, he was quite a character. He walked everywhere. He was working in Paris when the Franco-Prussian War broke out, and he decided that Paris probably wasn't the best place to be and that he would go to Italy and that he would walk to Italy. And so he set off, but he hadn't made it very far before someone overheard him mumbling to himself in German. And so he was arrested on suspicion of being a Prussian spy. And of course, when they looked in his bag, they found all his notebooks with the mathematics in them, and that convinced them that he was carrying all these secret coded messages. So they popped him in prison, and he was there for about a month before his colleagues in Paris realised, and they came to get him out of prison. When he was released, apparently he said that he thought that mathematicians were quite suited to life in prison because it gave them plenty of time to think. And I often think of this story when I'm loaded up with teaching administration, and I think, wouldn't it be nice just to have a little bit of time to think? Nothing serious, just a little bit. And this is the picture inside his book. I took this picture when I was visiting someone in Italy, and I was super excited to be able to, actually look through these old books myself. All right, so what did Lee do? He showed that if a partial differential equation is invariant under a one-parameter Lie group of point transformations, then the number of independent variables can be reduced by 1. All right, so what does this mean? Let's think about if we had a problem in 2 dimensions, so we're working on the plane, and let's say that the problem and the way we described it and modeled it didn't care whether we turned the axis one way or another. So we can rotate through any angle and the problem looks the same. Now, this is something that intuitively we know this means it's axisymmetric. And so what we would do is we would write down the problem so that it didn't depend on theta anymore. It only depends on the radial coordinate. And so we've reduced the number of independent variables by 1. Now, this is a really intuitive example of how you can think about, if there's some kind of invariance, so it's invariant to rotations, you can decrease the number of independent variables by 1. But what these symmetry methods do is they provide you with a framework where you can systematically search for all the symmetries, no matter if they are obvious from either your equations or from the geometry of the problem or not. And you can find all these weird kind of symmetries that you can use to reduce the number of independent variables in your problem. Okay, all right, so another person who was working in the area at the time was Nota, and she's arguably one of the most significant women mathematicians, arguably the most significant women mathematicians in the 20th century. She spent a lot of time using symmetries to find conservation groups of differential equations. And Nota's theorem is possibly one of the most important theorems in guiding modern physics in the last century as well. Oh, and if they ever make a movie of Nota's life, I think they should ask Emily Blunt to play her. All right, so now I'm going to tell you how symmetry analysis works, and I'm going to do it in quite a bit of detail because, as I said, this is where I find the fun. So I'm going to do everything in terms of the heat equation for two reasons. The first is that the heat equation is familiar to most of us, so I think we can all feel a little bit comfortable with it. But secondly, the heat equation is one example where you can actually work through all the way to the end. You can find the solutions here. All right, so what do we do when we look for classical Lie point symmetries? We look for transformations of this type. Can you see my cursor, Phil? Yep.
Yeah, I can see it.
Okay, thanks. So we look for transformations of this type, and we're going to require that our equation that we're interested in, so the heat equation, is invariant. And by that, what I mean is that in the old coordinates, it should look like the heat equation, of course, but in the new barred variables, it should also look like the heat equation. So we're going to have this requirement here. Now, when we have that requirement, what happens is you get this overdetermined linear system of PDEs to solve for U, big X, and big T. And the big U and the big X and the big T are the things here that characterize the transformation. Now, it's overdetermined, so you can't always solve it, but if you can solve it, then that information allows you to find out what the invariant quantities are in your problem, and then you can reduce the number of independent variables by 1. So normally what happens with the PDE is you reduce the number of independent variables by 1. So in the case of the heat equation, where we've got 2 independent variables, we're going to go down to 1 independent variable, and that will be an ODE, and hopefully that's easier to solve. Now, these are called classical point symmetries. The point part comes from the fact that these things that characterize the transformation depend on X and T and U. And for example, they don't depend on things like the derivatives of U. If they did, they'd be contact transformations or Lie-Backlund transformations. The classical point comes because these are the symmetries that Lie first talked about. Right. Okay, so I'm going to look at the example of the heat equation, and I'm going to do it in a bit of detail just so that you can see how it works. Now, here's the heat equation. We want to change it to the barred variables, or compare the bar to the unbarred variables. So we can use the Jacobian to figure that out. And here it is. There's a lot of stuff here. Now I just need to move something on my screen. There's a lot of stuff here, but what I've done is I've grouped the right-hand side, which is all the original stuff in the original variables, into coefficients of different powers of epsilon. So this bit at the start is epsilon to the power of 0. Here's the epsilon term, all in these big square brackets all the way to the end, and then I'm going to ignore the epsilon squared terms. Now, if we want the heat equation to be invariant so that it looks the same in both sets of variables, that means what I want to do is keep these blue bits here, and this stuff that's all in these square brackets should be identically equal to 0. Now, the stuff in the square brackets I've grouped together in terms of coefficients of the different derivatives of U. So subscripts here are derivatives. I've grouped them together in terms of the coefficients of the different derivatives. And if we want this to be identically equal to 0 for all different values of these derivatives, that means each of these coefficients must individually be equal to 0. And this gives us our set of equations from which we can determine the big T and the big X and the big U. And because we can determine them, these are called the determining equations. Now you can see that we've got too many. There's lots of coefficients here that we're going to set equal to 0, so they're overdetermined. Maybe we can't solve it. In the case of the heat equation, we can. Start with the easy ones. So this one here, for example, tells us that big T is independent of U. This one here is going to tell us that big T is independent of X. And so you start with these easy ones and you can work your way up, substituting into the other equations and integrating as you go. Now, as you integrate these partial differential equations, you're going to add a bunch of constants of integration. And as I said, for the heat equation, you can work it all the way through to the end, and here's the answer. So we add 6 constants of integration. That makes this a 6-parameter symmetry group, and they're labeled as the C's here. And you can see, indeed, just as we knew would happen, this big T here, there's no X and no U here. It's independent of X and U, just as we knew it would be. All right, now if you're braver than me and perhaps a little bit crazier than me, you can take this giant symmetry group and try and do something with that. But typically what we do is we pick on 1 or 2 of these parameters at a time and set all the rest equal to 0. And so what I'm going to do now is show you some examples of different symmetries for the heat equation that probably you've seen before, but perhaps you didn't realize that they are symmetry groups, and you can find them with symmetry analysis. Okay, so the first one I'm going to talk about is what happens if we set C1 to be non-zero and all the others equal to 0. And what happens then is we get big X is a constant, big U is a 0, big T is a 0. And this is what our new variables look like. It's just translations in space. So this tells us that the heat equation is invariant to translations in space, which we know already and makes perfect sense. All right, let's do another one. Let's go back. What happens if we choose C5 to be non-zero and all the rest equal to 0? Then we have something like this. And this tells us that the heat equation is invariant to translations in time. And this is something that we know as well. It makes perfect sense. All right, those two aren't very exciting. We can do something a little bit more exciting by keeping both the C1 and the C5, and we get something like this. What we can do with this information is we can find out a new invariant quantity. The new invariant quantity is a combination of the 2 original independent variables here. And many of us will recognize that this is just the traveling wave coordinate. So the fact that it's invariant to translations in space and time tells us that we can rewrite the equation in terms of the traveling wave coordinate. The dependent variable stays the same as the original one, but now it's a function of Z instead of X and T. And we can rewrite the heat equation, which is a PDE, to make this equation, which is an ODE. And this one is one that we can solve, and we can get the traveling wave solutions for the heat equation from there. All right, I'm going to tell you one that's a little bit more exciting, and this one I'm going to work through in even more detail, just so you can see how it works. All right, I'm not going to go back, but if we set C3, so that the third constant, the third parameter, equal to 1 and all the others equal to 0, this is what we get. We get a big U is 0, a big X is X, big T is 2T, and this is what the transformation looks like. Now, some of you will also recognize this one. This is the Boltzmann stretching transformation, and this is quite commonly used in problems of physics as well. All right, now I'm going to show this one in detail just so you can see how it works. Let me just see here. Okay, so here's our big T, our big X, and our big U. This is how we would write our symmetry, which doesn't matter too much for now. But what we can do with that information is we can write down a characteristic equation. So we're going to have dt over big T, dx over little x, du over 0. And then I can take pairs from this characteristic equation and integrate each of those pairs separately. So if I take the 2 independent variables first, I can integrate that as normal. And the constant of integration is what's going to become our invariant parameter, and that's going to be our new independent variable for our problem. The u on the denominator, whoops, sorry. Oh, yeah, 0 on the denominator here just tells us that the new dependent variable will be the same as the old dependent variable. All right, so here's our new variables. Here's our heat equation. So we're going to change to our new variables. All we need to do is calculate the derivatives that we need. So here comes the time derivative. And then we're going to calculate the space derivatives. And yes, I have sped this up. I figured if students could do it, I could do it as well. All right, so we've got the time derivative, the second derivative in space, which are the two that we need for the heat equation. We substitute them in. And then you'll see what happens is that any trace of those original variables will cancel out as long as we've done everything properly. And then what we've done is we've turned our heat equation, which is a PDE, into this ordinary differential equation. Now this is one that we can solve. I can rearrange this a little bit. And then after rearranging, I can integrate once. And here's what happens after we integrate once. And I can rearrange it again, which allows me to integrate it once more. Okay, now many of you will recognize this. This is the error function. So we can write this solution using the error function. Now this is the solution in those new variables that we're using. But of course, now we can switch back to the original variables. And so this is how you get the error function solution to the diffusion equation. And I think lots of people know that the error function is a solution to the diffusion equation, but I think not many people know exactly where it comes from. And this is where it comes from, and I think it's lovely. Okay. All right, so that's classical symmetries. Now I'm going to talk about non-classical lead point symmetries. So non-classical symmetries were first proposed by George Bluman. Now he was a PhD student working with Julian. Julian was an applied mathematician and aeronautical engineer at British Columbia. George Bluman has an interesting story. His parents were among those Jewish people who were given life-saving visas by the Japanese vice consul Sugihara to escape during the war. The other interesting thing about Bluman is that when he was working on his PhD, he was developing this theory of non-classical symmetries. And a lot of work at the time was going on in Russia. And of course, that communication was a little bit tricky there. But Julian went to visit somebody in Moscow, and he came back with a copy of a book by the Russian Ovsyannikov, brought that back to Bluman, and Bluman translated it from Russian to English in 4 weeks and realized that what Bluman was doing was actually new stuff. I don't know many PhD students these days, including myself, that will have translated a book from Russian to English. Anyway, this is the paper that came out of George Bluman's thesis. It came out in 1969, and it's one of the most highly cited maths papers from 1969. And it's just one of those lovely papers that's got all these really carefully hand-drawn little pictures in them. I just think it's lovely. Anyway, what Bluman proposed was that when you do the classical symmetry analysis, you should incorporate this extra restriction. Now, sometimes when you incorporate this extra restriction, it allows you to find more solutions to those determining equations that we were looking at before. Now, it seems counterintuitive that an extra restriction would give you more solutions. But what it does is it restricts you to the surface of invariance of an unknown symmetry. And that means you don't need to find the solutions over the whole space. All right, so let's talk about how this works. So for non-classical symmetry analysis, what you do is you do the same thing. You look for transformations of this type again. And again, you want the equation to be invariant. So the way it looks in the original variables should be exactly the way it looks in the new variables. But also, in addition to that, you want it to satisfy this invariant surface condition here. So this puts a condition like a relationship between the big T and the big X and the big U. What happens there is you get an overdetermined system of PDEs to solve again, but this time it's nonlinear, and so it's much trickier. Now, yes, it's tricky. It was made a little bit more straightforward by Clarkson and Kruskal, who suggested the direct method, and that made things a little bit more straightforward. This is the same Peter Clarkson and Martin Kruskal that Nalini mentioned in her talk as well. Okay, so I'm going to tell you some details about this, not as much as I did before, and I'm going to do it for this equation here. So it's a reaction-diffusion equation. not doing it for the heat equation because the heat equation doesn't have any non-classical symmetries. So we'll use this one. And now we start to see some pictures, more beards, but still some pictures of people that we're more familiar with. So the complete non-classical symmetry analysis of this class of equations was completed by two groups at the same time. One of the groups was Danny Arrigo, who was postdocing with Jim Hill and Phil Broadbridge at the time at Wollongong University. And the other group was Peter Clarkson and Liz Mansfield, and they're at Kent. And they'll be well known to many people here too. Liz originally comes from Sydney, and Peter and Liz will often visit Australia and come to Australian conferences, and they've been to ANZIAM a few times in the past. Okay, so I'm going to look at this particular equation. So we've got a u cubed for our reaction term, and we're going to do something similar to before. So we use the Jacobian, we can transform the equation and see what it looks like and compare them. So the ones marked in blue are the ones that we want to keep. This would say that the equation looks the same in both sets of variables. The stuff in the square brackets is, again, what we want to make equal to 0. This time we do it a little bit differently. One thing we can do is we can rearrange the equation for the second derivative in x. And then anytime the second derivative in x appears here, we can replace that with the rest of the equation that we're interested in. The next thing we can do is we can set big T is equal to 1 and rearrange the invariant surface condition. And now wherever a time derivative appears, we replace it with this right-hand side here of the invariant surface condition. And any of the mixed derivatives we can replace with the differential consequences of the invariant surface condition. Now, there's two consequences of this. The first is, for example, you can see if I take this ut here and replace it with this stuff here, now it's becoming nonlinear. I've got this u sub u times by u, for example. And so these determining equations become nonlinear. And not only that, what happens is all the derivative terms, like these ux terms and uxt terms, they all turn into coefficients, or the rest of the stuff, I should say, turns into coefficients of different powers of ux, so the first derivative of u with respect to x. And what you want to do is you want to set all those coefficients again equal to 0. You've got nonlinear set of determining equations, and you can find the big U and the big X and the big T if you're lucky. Okay, so let's look at the answer for this one. So when you've got this U cubed reaction term, this is what the big U and the big X and the big T look like. Big T is 1 because that's the way we designed it. We set it that way in the invariant surface condition. And now often you use these symmetries in a slightly different way. What we can do is we can take the invariant surface condition again and rearrange it and substitute in the big X and the big U. And then we notice that we've got this time derivative here and this time derivative here. And these two things are the same, which means we can make this stuff here on the right-hand side equal to this stuff here on the right-hand side. And now we've got a pseudo ODE. So no time doesn't appear anywhere and time derivatives don't appear anywhere. So we can integrate it like an ODE. The only trick is when you add your constants of integration, they won't be constants, they'll be functions of time. And you can find out that time dependence by substituting it into the equation that you're trying to solve. So that's how non-classical symmetries work. Okay. And that's what I'm going to say about that. All right, so let's move on to the two example problems that I wanted to tell you about. So the first one is, what tricks can you do when you have a partial differential equation with some arbitrary functions or a arbitrary function in it? And the other problem I'm going to talk about, I've talked about it before, but I'm going to talk about it again because it's pretty cool, is this problem from math biology. So let's look at the first one first. All right, so let's imagine we have a differential equation and we've got some arbitrary function, and this is the one I'm going to use as an example. So it's a u squared 1 minus u. This is what it looks like. It's got roots where u is equal to 1 and a repeated root where u is equal to 0. Kind of looks a bit like a logistic, but kind of pushed to the side. And the question we might ask is, can I find analytic solutions to this equation, and what forms of that arbitrary function will allow me to find analytic solutions to this equation? So what you can do is you can keep that function arbitrary and start down the path of classical or non-classical symmetry analysis, And then if you're lucky, what will happen is you'll get a differential equation for your arbitrary function. And what that's telling you is if you're even luckier, you can find solutions to that differential equation for your arbitrary function. And if you're even luckier again, those forms of that arbitrary function will allow you to find additional symmetries. And if you're still lucky, they'll let you reduce the PDE to an ODE and then hopefully solve it, and then you can work your way back. So we worked on this problem a little while ago, this particular one, and I could find 3 solutions to this differential equation for f, and these are the ones I found. F is equal to x squared, tanh x, and a tanh squared and a tan squared. And I was lucky in that each of these 3 led to additional symmetries, and they each led us to be able to solve this PDE at the top. So we can write down analytical solutions for that. Turned out a couple of years later, I missed a couple. There's not actually 3, there's 5. So Natalia Ivanova and Sophus a few years later found the 2 I'd missed. There was a cough squared and a 1 over x squared. Okay, so why would we care? Now, I'm a little bit crazy, as I said. So I think any time-dependent analytic solutions of a nonlinear PDE that you can find are good and exciting and fun. But I'm going to focus on one of these solutions and tell you where perhaps it might be applicable. So I'm going to focus on this tanh squared one here. All right, so let's work our way through this slide. So here's our differential equation that we're going to work with. We've got this reaction term here that's cubic. It looks a bit like a pushed over logistic function. Let's go back and look at it for a minute. So these kinds of reaction terms are often used in macrobiology, as I said, for cell proliferation or population genetics, or Phil gave a talk a little bit earlier about a fisheries problem, which uses the quadratic term, but it's a similar kind of shape to this. And this is the arbitrary function, the spatial dependence that we're going to add into the reaction term. Now, for this equation, we can find this solution here. This is the analytic solution. This tanh squared function, what that looks like is, it looks like this picture down here in the bottom left corner. So that's telling us kind of that the reaction term, in terms of the dependent variable part, is turned on in these outside regions of the range, and it's turned off in the inside part of the range. So you've got diffusion in the middle, but nothing else, and you've got diffusion and perhaps proliferation or births and deaths or whatever on the outside of the range. So perhaps it's kind of a barrier problem where there's maybe no food in the middle here. This is a picture that I pulled out of a paper by Wang Jin and Scott McHugh and Matt Simpson and Catherine Pennington and a few others, I think. This is a picture of a scratch assay. What they're doing here is they've got a cell colony growing happily, and then they scrape away the middle section. So this is the bit that's been scraped away, so that they've only got cells on the outside of these green lines and no cells on the inside of these green lines. And then what they do is they watch how the cells recolonize that middle section here. Now, this problem that they were thinking about here didn't have a lack of food in the middle. But for example, you can imagine a problem where you did something like this, took away all the food or the nutrients in the middle, and then you can see what happens. This is a plot of the solution. So you can see the population is high at the edges of the range, and then it manages to recolonize that central region. And you could do things like you could play with the width of this barrier. You know, if you make it wider, does it take longer for the cells to recolonize in the middle? Or is there a threshold width beyond which the cells just can no longer manage to recolonize the region? And you can investigate that just by looking at all the different parameters. Obviously, I took those kinds of parameters out of this function when I plotted it here. Okay, so that's all I was going to say about this first problem. All right, so this is the second one I want to talk about. This is a problem of fertilization waves on amphibian eggs. So in the 1980s, it was first observed that when an amphibian egg was fertilized, there'd be this wave of calcium ions that would travel over the surface of the egg by a calcium-induced calcium release mechanism. So this is like, this is assumed to be the fertilization point here. And then the orange and the yellow represents increased levels of calcium ions on the surface of the egg. So the point of these calcium ions is to stop any additional sperm going into the egg, and so they stop polyspermy or the duplication of genetic material. So this was first observed in the 80s. They wrote down an equation or a model that they thought described it. And it's just a reaction-diffusion model, but it's on the surface of a sphere, which makes it a bit more interesting as well. These numbers here, I should say, are time in seconds. So this is after 45 seconds. So it doesn't take really long for this to happen. Okay. All right, so this is the model that they wrote down. It's got a diffusion term and it's got a reaction term. This is the coordinate system in the bottom left here that we're going to be working in. So we'll work in spherical coordinates. We're going to make the sperm entry point at the top of the egg, so a different orientation than what's in the experimental picture here. But we'll put the sperm entry point at the top, and then we're going to assume symmetry in the azimuthal direction like this. So we're just going to assume that this wave of calcium ions comes all the way down the outside of the egg to the bottom hole of the egg. This picture here at the bottom right is a schematic or a little sketch that was drawn from experimental data. And it's supposed to kind of indicate how the wave of calcium ions progresses around the surface of the egg. So this is the model that they wrote down. This is the diffusion term. They used constant diffusivity, which is not quite the way I've written it here, but they used constant diffusivity, which means we just have the Laplacian on the surface of the sphere. For the reaction term, the arguments about this come from this picture here at the top right. So this wiggly line that goes up like this represents the release of calcium ions from the stores near the surface of the egg. This straight line that's going down here represents the resequestration of the calcium ions back into the stores near the surface of the egg. And if you combine those two processes, the wiggly line up here and the straight line down here, you end up with a curve like this. So this is telling us that in this region here, so below some threshold level, the calcium ions are absorbed back into these stores on the surface of the egg. But if you get above this threshold level, then the calcium ions are released from the stores near the egg and the wave will progress. Now, there are lots of different papers that have looked at this wiggly curve and written down different functions that will model that curve. But of course, the most simplest one and straightforward one that will fit the bill is a cubic. Now, here's a cubic here in this red line. Now, if the reaction term is cubic and the diffusivity is constant, then there's no classical or non-classical symmetries that can help us find any solutions in that case. But if we take this dashed line instead, which is not a cubic, but it's cubic-like, and it certainly has the same kind of characteristics that are shown in this figure here. If we take this dashed cubic-like term, and then instead of taking a constant diffusivity, we take this dashed diffusivity here, so it's non-linear, then we can find a non-classical symmetry that allows us to find a solution. So this dashed line here is a combination of tanh functions. This dashed line here is some kind of rational function in U. And we can find a solution, or we can find a non-classical symmetry that will help, I should say. Now, this non-classical symmetry is kind of special. What it does is it allows you to separate, completely separate the time dependence of the problem from the space dependence of the problem. And what you end up having to do is solve an ODE. As we saw before, you reduce the PDE by one independent variable. So we're going to move to an ODE, from a PDE to an ODE. And that ODE happens to be the Helmholtz equation. So now all we need to do is solve the Helmholtz equation on the surface of the sphere, which we know how to do. We are mathematicians. And here it is. I can write down the analytical solution. I haven't written it in, so it's quite long. But here's the solution mapped to the surface of the sphere. So blue are regions of low calcium concentrations, and the yellow and the red are regions of high calcium concentrations. These pictures are at non-dimensional times 0, 3, 6, and 9, and 9 corresponds to about 40 seconds. So not too far off of the 45 seconds that's in this picture here. And I've got a little video that shows what's kind of satisfying as well. All right, so the sperm entry point's at the top, and you can see there's a wave of calcium ions that's going to come down over the surface of the egg, starting at the top and finishing at the bottom. Okay. All right, so having an analytical solution is kind of interesting in this scenario. I mean, I think it's cool because I love solving nonlinear PDEs, and doing it on the surface of the sphere was even cooler than normal. But you can answer questions like this: how much calcium is released from the pole where the sperm entry point is, and how much comes from the stores of calcium near the cortex, near the surface of the egg? And you can work this out because all you need to do is integrate your solution, which you have. You can write this down. Integrate your solution around the pole at the top of the egg, and that will tell you how much calcium is coming from the pole, and the rest of it's going to come from the stores near the egg. So that tells us that about 20% of the calcium ions come from the pole at the sperm entry point, and about 80% comes out from the stores on the egg surface. The other thing we can do is I mean, you wouldn't maybe expect it in the experimental papers, or maybe if they plotted those kind of graphs that I showed before. But certainly in the numerical papers I read where they solved this, they would give you all the parameter values for the problem, except for the one that controls the strength of the reaction term. So how big is that cubic function that we're using? None of them would tell us what that parameter value was. By matching up the timescales of our solution with the timescales of the experiment, you can infer what the value of that parameter is and how strong the reaction term was. That was kind of a cool little project. Okay, now if I could see you, I might see some of you saying, all right, well, it's all well and good to solve this problem, but you made up an equation that you could solve and write down the solution to that. You didn't actually solve the one that they wrote down. So does this analytical solution match the numerical solution to the original problem? All right, so here I've plotted our analytical solution with the numerical solution. So the analytical solution is the solution to this PDE here. We've got that nonlinear diffusivity and the cubic-like reaction term. In this figure here, the vertical axis is the concentration of calcium ions, and the horizontal axis is the angle around the egg. So where theta equals 0, that's at the top of the egg, and theta equals pi, that's at the bottom of the egg on the other side. And you can see that the calcium ion concentration is much lower at the bottom, and that it increases as time goes on, as you would expect. This right-hand picture is the numerical solution to the original model that was proposed in the Chia paper. So it's got constant diffusivity and a cubic reaction term here. And of course, the initial conditions look a little bit different because we just started with the standard shape here. But you can see that after very little time, the solutions look almost identical. The only real difference between the two solutions, or the solutions to the two problems, is that the numerical solution travels slightly faster than the analytical solution to this slightly different problem. Okay, all right, so I'm coming to the end of the things that I wanted to say, and what am I trying to say? So I've been trying to convince you that analytical solutions are actually useful, and hopefully I've convinced you of that. You can use them. One thing I haven't said is you can use them to check your numerical solution. So if you can find an analytical solution to perhaps the base case of your problem, you can use that to check your numerical code before you ramp up the numerics to do something a little bit more fancy. They can give you additional information, and you can get direct insight to which are the important parameters in a problem and what those parameters will do. Now, if I've convinced you that analytical time-dependent solutions to nonlinear PDEs are important, then hopefully I've also convinced you that symmetry techniques can be a useful way for finding these types of solutions. And I reckon they're fun. I really like doing these things. I really like finding those kind of obscure, weird solutions to nonlinear PDEs. And there's that really wonderful moment where you have your, complicated analytical solution that you can write down, and then you can substitute it into your PDE and you just see it all work out just beautifully. It's just really lovely. All right, so now I get to thank a couple of people. So most of the people that I was working with on the things I've talked about today are in this picture. Maureen Edwards at the University of Wollongong, John Wojcicki, who's now at Wits in South Africa and Johannesburg, Phil, of course, not with a beard, but with a moustache, myself, and Graham Williams, who's retired now from the University of Wollongong, sporting another beard. All right, now if you'll indulge me just for another couple of minutes, I've got 2 more slides I wanted to show. So the first one is a shameless advertisement. I've got a DP project. I'm looking for a PhD student. We're going to work on looking at pattern formation of precursor films for ionic liquids. It's a joint project with a really clever bunch of experimental physical chemists. So if you know anyone who's looking for something exciting to do for the next 3 years, please send them my way. Now, the last slide that I'm going to leave you with, it's a quote from Sophus from a letter that he wrote nearly 140 years ago. And I guess this comment really sums up what I was trying to get across in my talk. And he wrote, he was lamenting at the time that his methods weren't becoming more widely used, I think. He said, if only I knew how to get mathematicians interested in transformation groups and their applications to differential equations. I'm certain, absolutely certain, that these theories will sometime in the future be recognised as fundamental. That's me. That's all I wanted to say.
Yeah, thanks, Brian. If you have questions, please type them in the Q&A. To lead off, Matt Simpson has asked about what you can do with boundary and initial conditions, and can they be varied with this sort of
Yeah,
thing?
okay. So that's a sneaky question that I avoided. When you're looking at the determining equations are already over-determined. You can add the boundary or initial conditions in there as well, but it becomes even worse, and oftentimes you can't find a solution if you're going to be specific about the initial conditions and the boundary conditions. Joanna Goard, who also is now retired from the University of Wollongong, did some work about making it better or easier, or those are both the wrong words, but being able to incorporate more easily the boundary conditions and initial conditions, but it's still really tricky. And so often what you do is you ignore the initial conditions and you ignore the boundary conditions. You do your symmetry analysis, you look for what kinds of solutions you can find, and then you see, do any of those make sense? And, you know, do any of those have sensible initial and boundary conditions, I guess?
Yeah, there's a
yes, I avoided that one.
Another approach from Neville Folks and friends that you can find level sets for boundary conditions, and from an analytic solution, you can find a level set that satisfies a given boundary condition, and then find which geometry you can put in there. So Q&A, I've got some more. So I think that kind of answers what David was saying. David is asking, if you're not lucky, can this analysis still provide insight into the problem?
Yeah, so the answer to that is yes, thank goodness. Or actually, it depends maybe what lucky you're asking about. Lucky with initial conditions or boundary conditions, then yes, you can still get a lot of insight. If you're not lucky, maybe you're talking about when I was talking about the arbitrary functions. Yeah, so some equations you'll put in the arbitrary function, and then you just can't find any sorts of arbitrary functions will allow you to get a symmetry. And maybe then it can be helpful to change up your equation just a little bit more and see if you can add any more arbitrariness or anything like that to try and get something useful out.
Yeah, I can say also we can usually solve problems with standard Dirichlet boundary conditions on standard geometries. That usually works out. But sure, you're quite right. Of course, there are some initial boundary problems we never solve with this kind of method, except if you've got a nonlinear PDE that can transform to a linear one. Sometimes we use those. But certainly you can use this to test a numerical method that can then go on to solve the problem you're really interested in.
Yeah, for sure, that's right.
So I'll keep them coming. We got, let's press Q&A again. So that seems to be the lot. Oh, Paul Leopardi, he can, unmute and make yourself heard or type in.
You can see his question here. It says, your examples had 1D independent variables. Do you mean like in one dimension? I only had one space dimension.
Oh yeah, sorry, I didn't scroll enough. Yeah. No, it's not true. There are 1D independent variables. I think you can see from the egg problem we're talking about diffusion on a sphere. It's certainly multi-dimensional.
Yeah, so if you're talking about one-dimensional in space, that's all I did, yes, because that's all I was going to show today. But you can have any number of dimensions, of course. And in fact, that non-classical symmetry that I was using to solve that amphibian egg problem, that non-classical symmetry actually works truly in any number of dimensions and in any coordinate system. So we actually solved that problem as well on the surface of the sphere, but not taking azimuthal symmetry. And you can actually get spirals on the surface of the egg as well, spiral solutions. I didn't talk about it.
Right, so these questions are getting harder. Are there any harder ones out there?
I need hard ones.
I think Bron would prefer hard ones to easy ones, if you can keep them coming.
Very easy ones.
Oh, that's good. That's the spirit. Well, see if I can scroll a bit more. Okay, thanks everybody, and thanks Bron for a very nice self-contained talk with some nice applications, and really appreciate it. Let's give.
No worries, my pleasure. Thank you.